In this question, we intend to simulate this simple example, having been selected about the strength of materials in the Abaqus software. As you observe in this picture, one steel bar having a length of 2 meters has been connected to an aluminum bar that is 1 meter long. Here, a force equal to 15 kilonewton is applied to the middle of the steel bar. As it is quite clear in the picture, this bar is composed of 3 segments. 2 segments are of steel and 1 of aluminum. The purpose of this problem is to calculate the displacement of points B and C using the Abaqus software and strength of materials, and following that, comparing the results obtained from the Abaqus software with those gained from the strength of materials. I will enter the Abaqus software for simulation. I will click on Create Part. I intend to create a geometric shape of the bar. Here I will select the modeling space as 3D deformable. From here select Via and Planar. Enter approximate size equal to 10 and continue. I will draw a horizontal line and enter its length equal to 3 meters. As you observe in this picture, the bar is composed of 3 parts. The left bar is of steel, the middle one is of steel, and the bar on the right side is of aluminum. So I will divide this bar into 3 segments. I will click on Tools menu, select Datum. From here select Point and then Offset from Points. Select this point and enter offset equal to 1 meter. In the next step, I'll select this point, enter offset equal to 1 meter. In the next step, I will click on Tools menu, select Partition, from here Edge, then select Midpoint, Datum point, select this point and click on Create Partition. In the next step, I will select this bar, then this point and click on Create Partition. In this manner, the bar was divided into 3 parts. In the next step, I will enter Property module. Click on Create Material. Here I intend define the properties of steel. I will click on Mechanical menu, select Elasticity and Elastic. The Young modulus of steel is 210 gigapascal, so I will enter that equal to 210 multiplied by 10 to the power of 9 Pascal. The Poisson ratio is equal to 0.3. OK. I will click on Create Material again. Here I intend to define the properties of the aluminum. I will click on Mechanical menu, then on Elasticity and Elastic. The Young modulus of aluminum is equal to 70 gigapascal. And the Poisson ratio of that is equal to 0.33. I will click on Create Section. Here, select Beam and then Truss. We use truss elements in this question, but there will be no problem even if we use beam elements, and the results gained will make no difference. Here I will select Truss and continue. I will select Steel material. The cross section of steel is equal to 2 multiplied by 10 to the power of negative 4 square meter. I will click on Create Section. Select Beam and then Truss and continue. I will select Aluminum material. The cross section of aluminum is equal to 6 multiplied by 10 to the power of negative 4 square meter. I will click on Assign Section, select the left and middle bars. Done. Select the steel section. Okay. In the next step, I will select the bar on the right side. Done. Then select aluminum section and OK. Here you can observe the model in a three-dimensional mode. In the next step, I will enter assembly module. Click on create instance. Enter the bar into the assembly section and OK. In the next step, I will enter step module. Click on create step. Here select static, general and continue. Since this problem is linear by nature, I will select off option. But even if you select on and consider that as a non-linear problem, it will be okay and the results obtained don't make any difference together. However, since here it's a linear problem, I will select off option. Time period is equal to 1 second and OK. In the next step, I'll enter load module. Click on create boundary condition. Select displacement, rotation and continue. I will select the left and side ends of the bar. Done. As you observe in this picture, the left and right ends of the bar are absolutely fixed, so I will close all conditions of displacement. In the next step, I will click on create load. Here select step 1, then concentrated force and continue. I will select this point. Done. Enter the force equal to 15,000 Newton and OK. In the next step, I will enter mesh module. Click on seed part, enter approximate global size equal to 0.01 meters. Click on mesh part and yes. In the next step, I will click on assign element type. Select the whole of the bar. Done. Put the element family on truss and OK. In the next step, I will enter step module. Click on tools menu, then select set and create. I will name the set point B. Continue. Select this node and done. In the next step, I will click on tools menu again. Select set and create. Name this set point C. Continue. Select this node. Done. I will click on create history output. Continue. Here select set, then point B. Then select U1 or the same displacement directed at x-axis and OK. I will click on create history output once again. Continue. Here select set and then point C. Here select U1 and OK. Here I will save the model. I will enter job module. Click on create job. The analysis was done successfully, so I will click on result. The simulation of this problem is aimed at calculating the displacements of B and C points using the strength of materials and the Abaqus software. Here we will calculate displacement of these 2 points using the strength of materials and then compare the results obtained from the strength of materials with those having been gained from the Abaqus software. In this picture, as it's observed, the problem has been solved using strength of materials. Here, using the simple and basic formulae of the strength of materials knowledge, we can easily solve this problem. The formulae having been used here are respectively as follows. The first one is related to the stress formula, and as you know, it is equal to F divided by A. Actually, F stands for force and A stands for area. The next one is Young modulus formula, and it is equal to stress divided by strain. And finally, the next formula having been written here is a strain formula, and it is equal to change in length divided by the initial length. If you simplify these formulae, you will get the formula delta X is equal to FL divided by EA. And we use that for calculating the change in length of materials. Here, as you observe, the displacement of point B is constant, meaning that the change in the length of the component 1 is equal to the sum of the length change in components 2 and 3 together. And the formula of which can be observed here. Here the quantities of F1 and F2 have been calculated, and F1 is equal to 10,000 Newton and F2 is equal to 5,000 Newton. F1 is the force applied to the component 1 and F2 is the force applied to both component 2 and 3. In the next step, the displacement of B point has been calculated. Here, the quantity of force is equal to 10,000 Newton. Young modulus is equal to 210 gigapascal, and the cross section is equal to 2 multiplied by 10 to the power of negative 4. The displacement of point B has been calculated and is equal to 0.23809 multiplied by 10 to the power of negative 3 meters. Now we intend to calculate the displacement of B point using the Abaqus software. I will click on Create XY Data, select ODB History Output and continue. Here I will select point B, click on Save As and OK. Here you observe the displacement quantity having been obtained from the Abaqus software. The displacement of point B is equal to 0.000238095 meters. As it can be observed, the result obtained from the Abaqus software is exactly similar to those gained as to the strength of materials. In the next step, we intend to calculate the displacement of point C, and it is equal to 0.119047 multiplied by 10 to the power of negative 3 meters. having been done using the strength of materials formula. Now we want to calculate the displacement of point C using the Abaqus software. I will click on Create XY Data, Continue. Here select point C, click on Save As and OK. Here the displacement of point C having been obtained from the Abaqus software is equal to 0.000119048 meters. The displacement of point C obtained from the strength of materials is equal to 0.119047 multiplied by 10 to the power of -3 meters. As it can be observed, the results obtained from the Abaqus software are perfectly similar to those gained in the strength of materials, and as you observe, these results are very precise indeed.